we're not going to do any math. We're actually going to look at reactions. So, let's talk first. Alright, on Friday, I went over the difference between a solvent and a solute. What is the difference?
So solute is being dissolved.
Yes.
The solvent is like a dissolving property.
Correct. So, there are attractions or an interaction that is holding your solid particles together. Those attractions or interactions must be overcome in order for the solute to dissolve. So in other words, you say this is my solute. It's all together. I must break those attractions and form a new attraction between my solute and my solvent. That's the only way that a solute will dissolve in a solvent. I also mentioned on Friday that normally our solvent in this chapter is going to be water. So, let's talk about ionic compounds. Refresh your memory on what an ionic compound is. An ionic compound is a metal and a non-metal, or it's a positive charge and it's a negative charge. So what happens is when I break those apart, water surrounds it so that if it's the positive metal, the negative charge on water orients itself around that positive charge. The negative charge on water is your oxygen. It's polar. So this is my negative pole, this is my positive pole. So oxygen is facing my positive charged metal. My negative charged non-metal is surrounded then by water, but it orients so that the hydrogen is right next to that negative charge because opposite charges attract. Okay, so before we talk about solubility, we need to talk about electrolytes. Anybody know what an electrolyte is, other than the things in Gatorade?
It's a substance that dissolves in water to form solutions such as alcohol.
Correct. So an electrolyte is something that dissolves in water and forms a solution that will conduct electricity. Alright, so electrolytes are classified by how well they will dissolve in water. So if they completely dissolve in water, that means that solute breaks down into a positive and a negative. So that is what will conduct the electricity if you apply some external electric charge to it. So, strong electrolytes Strong electrolytes completely dissociate or break apart in water. A good example is sodium chloride. If you put it in water, it's going to break into a positive charged sodium, a negative charged chlorine. There will no longer be any sodium chloride intact molecules. So the compounds or molecules that will be strong electrolytes are going to be ionic compounds, so something with a metal and a non-metal, and strong acids and bases, which we talk about acids and bases in the second half of this chapter. weak electrolyte only partially dissociates in water. When I'm talking about a weak electrolyte, I use this double arrow to show that in solution, I have some of what's on the left and some of what's on the right, because it didn't all break apart. This is a weak acid. That's why it kind of looks funny. So it will dissociate some, but I will also still have some intact acid in the solution as well. So weak electrolytes are going to be weak acids and bases. And then non-electrolytes, they don't conduct electricity. So non-electrolytes don't conduct electricity. So we're about to be writing different types of reactions. With non-electrolytes, we leave them together as a whole molecule. We don't break it up into its corresponding elements. Another way to define a non-electrolyte is it's a molecular compound that will dissolve in water, but it won't form ions. An example is glucose, C6H12O6. We are going to focus on ionic compounds for the time being. So, ionic compounds are strong electrolytes, so they will dissolve in water, except those that are insoluble in water. So what I passed out to you is your solubility table. You have to memorize that. It will not be given to you on your exam. YouTube or Google, there are a bunch of different mnemonics that will help you remember those. Once you use them for a while, they kind of just stick automatically. Alright, so a compound is said to be soluble if it dissolves in water. A compound is said to be insoluble if it does not dissolve in water. And what happens is, if it does not dissolve in water, it forms a precipitant, which is a solid compound left in solution. So let's look at a few compounds before we actually apply this to reactions. Right, so using that table, let's predict whether they're soluble or insoluble. Lead to chloride. If you look at the top of that table, chlorine, bromine, and iodine are generally soluble, except when they are paired with silver, mercury, or lead. So this is insoluble.
When we have our exam, is there going to be a section just like this where you just have to tell whether they're soluble or insoluble?
Probably, yeah. So the rules I just read to you about chlorine, bromine, and iodine did not mention an exception dealing with copper. So letter B must be soluble. Calcium nitrate next. Again, if you look at the top of that table, you'll see that nitrate and acetate are generally soluble. There are no exceptions, so this is soluble. And then the last one, barium sulfate. Sulfate is at the bottom of the top part of the table. The exceptions include barium, so it's insoluble. Okay, why is this important? It's important because it's going to help us predict the products of precipitation reactions. So an example of a precipitation reaction would look like this. This is a precipitation reaction. I start with two soluble ionic compounds as my reactants. Because they are ionic and they are soluble, in solution, this is what they look like. They're all broken up. They're no longer together as potassium iodide or lead 2 nitrate. So we do kind of a double displacement type thing where the positive ion of one reactant now tries to form a bond with the negative charge of the other reactant and vice versa. Okay, so potassium tries to bond with the nitrate ion, lead to the iodine ion. When they do that, potassium nitrate, nothing really happens because it forms a soluble ionic compound. So in the reaction, it's still not really bound together. They're just hanging out. But my lead and the iodine, when they bond together, they form an insoluble ionic compound. Therefore, it precipitates out of solution, and I have a solid left floating in my liquid solution. So that is a precipitation reaction. So, let me give you some kind of steps to follow when you're trying to predict the products, and then we'll do some where you have to predict the products. If naming and forming compounds is something that you just totally skipped over and didn't bother learning, it's going to come back to bite you in this chapter. So basically, everything I do here is I'm going to undo my swap and drop. Okay, I'm looking at the ions that formed each of these aqueous reactants. Alright, so we're going to switch ions, so the cation from one reactant bonds with the anion from the other, and vice versa. Then to get the formula of the products, I'm going to swap and drop charges. Then, once you've predicted your possible products, you're going to determine the solubility of each of those products. If it's insoluble, it forms your precipitant, and so it gets the S behind it, like I did here. Okay? So don't confuse that when you're doing this. I see that happen a lot. They're like, oh, it's soluble, so it gets the S behind it. No. It's insoluble, so it forms a solid, and that is what that little S stands for. If both of your potential products are soluble, then no reaction happens because nothing's changing from one side of the reaction to the other. Like, nothing changed with potassium and nitrate here. I mean, yeah, it looks like they formed this compound, but it's aqueous, so they're really just floating in solution. So nothing's happening. Okay, then let's add here Of course, if you have something soluble, it gets the AQ behind it. The last thing you need to always do is balance the equation. Alright, so let's apply these steps to these two example problems. Alright, the first thing I would do is I would break all of these down into what ions they actually form. So then the next step is to determine our possible products. So potassium's gonna bind with chlorine, nickel to carbonate. So I'll have KCl and NiCO3. The 2 charge cancels because it's both 2. So these would be the formula of my possible products. But before I actually write them on the product side of the equation, let's make sure that I actually form a precipitate. KCl, soluble or insoluble? So it gets an aqueous behind it. What about nickel carbonate? It's insoluble, so it forms a solid. So now I can write these as for sure my products. I gave the soluble the aqueous, the insoluble the S. Now step 4 tells me to balance the equation. Looks like I just need a 2 right here. So I have 2 potassium, 2 chlorine, showing 1 of each there. Okay, let's do the next one. Same thing. Break it up into ions. Those are my 4 ions. So I'm going to do sodium with sulfate, lithium with nitrate, and it'll look like this if my products were formed. And check my solubility. Sodium sulfate is soluble or insoluble? Soluble, so it's aqueous. What about lithium nitrate? I believe it is also soluble. So you don't have to come and put these products over here. You can just write no reaction because nothing happened. No precipitant was formed.
Will the problem let us know that we're predicting precipitate reactions?
Not always. It'll either be a precipitant or an acid-base reaction.
Okay, so then we'll know.
Alright, let me give you a few more examples. Alright, y'all try those four. Alright, if you're not done, you can go ahead and write the correct answers. Or check your answers if you finished. On the second one, this Mercury right here is that weird Mercury. That 2 belongs to it permanently. Any questions? Alright, so this is where I will pick up on Wednesday, and I will send y'all an email about attending on Wednesday.
Is mastering due Saturday?